Okay, let's do our review. So start by pausing the video and writing down 8 to 10 bullet points that captures a course overview. Just do this. This is what we really want to do now is we want to take what we've learned and we want to integrate it. We want to synthesize it. We want to connect it. So in fact, just start from your memory, putting down what you think are the 8 to 10 major content areas of the course. And just see what you can come up with. This is not, you're not going to be graded on it, but just try it. Okay, here's what I did. Now, there's two ways I can think of to getting to this that you might have used to help yourself. One is the equation sheet. Just follow through what we did, all of this. And the other is just to go through Moodle week by week. And this is useful because it's a way of seeing everything we've learned in a holistic kind of construct, linked together, connected. And everything starts to make more sense when you do that. So anyway, week 1, electric force, week 2, electric field, week 3, electric flux and Gauss's law, two different things. Week 4, electric energy, potential energy, and electric potential. So just like force, you have to have two charges. Field, you only have to have one charge. Energy, you have to have two charges. Potential is like the energy field. What we call electric field is a force field. What we call potential is an energy field. Does that make sense? Maybe not. It takes time to kind of wrap your mind around these abstract concepts. It takes effort. Okay, so we're continuing. We're going to visit this, and you understand this through doing problems and watching the videos and reviewing the assignments. Then we did circuits. That's less abstract in a way. We studied capacitors, we studied resistors, we did resistor circuits, we did resistors and capacitors, RC circuits. We learned Kirchhoff's laws, all simple circuits. Spent about 3 weeks doing that. Then we moved on to magnetism. We talked about magnets, magnetic force, magnetic field, Ampere's law, Biot-Savart law, and magnetic flux. That relates to Faraday's law and Gauss's law. Gauss's law for electricity, Gauss's law for magnetism. And then finally, we went back to circuits, and we studied inductors, and then we did resistor-inductor circuits, inductor-capacitor circuits, and then resistor-inductor-capacitor circuits. And that brings us to the end of the semester. Okay, so that's the overview. Now, two things you're going to have to do on the exam is you're going to have to, through multiple choice questions and through essay questions, you're going to have to demonstrate your understanding of these concepts. And I'm not going to cover this in the review. You go back to the videos on field, go back to the videos on flux and Gauss's law, go back to the videos on electric potential energy and electric potential. The same way with circuits. There's a lot of videos on RC, RL, LC, RLC circuits. You need to do those, and if you've done the assignments thoroughly and thoughtfully, you're well prepared for the exam. Go over the equation sheet. Know all these, well, there's a few maybe you don't have to know, like this one. But go over these and make sure you know all these equations, right? Coulomb's law, the definition of electric fields, the way of calculating the electric field due to a point charge, the most general definition of flux, the definition and statement of the relationship of Gauss's law, This one we never covered, but it's the way of calculating electric potential energy, but this is how you do it for point charges. This is the definition of potential versus potential energy. It's a good essay question. Can you explain the difference between these two equations? And this equation, especially this one, that's the way of calculating the potential for point charges. Then we go into capacitance. Notice the definition of capacitance is different from the equation that tells you what determines the capacitance, right? These are the physical factors that determine capacitance. This is the definition of capacitance, just like this is the definition of resistance. This is the equation that tells you the factors on which the resistance depends. Those are all important distinctions, and they're all the subject of essay questions. I can give you this, and remember, one of the questions was, compare resistance to inductance. So there you have resistance. It's resistance to the flow current of electric charge, right? The ratio of voltage to current. When you get down to inductance, it's very similar. Not this equation. This equation is useful, but this is the one you want. Now, where is it? Yeah, the rewrite of this. L equals the voltage over the change in current. So resistance is a resistance to current. Inductance is a resistance to change in current. That's the parallel between those two quantities. And it all comes out of the equations. And then we have RC circuits and RL circuits. Same equation, either e to the minus t over the time constant, right? All of this, there are videos on all of this. And the relationship, we calculated inductance this way. We did use this equation in lab, right? We measured the flux using the area tool, divided by the current, and we got the inductance, and then we used this equation. So going through all these equations, and then some of them are hard, like the Biot-Savart law and Ampere's law. Right? There's a lot of content hidden in these equations. But it's a good essay question. I can give you the two capacitance equations. I can give you all these inductor equations and ask you to explain them. So make sure that you've reviewed the equation sheet, and if there's areas on here that you're just clueless about, then you should go back to those assignments, those videos, those labs, and study those things. Okay, let's talk about the midterm exam now and see what we can learn from what didn't go well on the midterm and avoid those problems on the final. Multiple choice questions. Study them, but don't just go through them trying to figure out what the correct answers are and answering them and then getting your grade. No, make sure you understand why the correct answers are correct and why the wrong answers are wrong. And it's sort of a quick way. You can go to an assignment and you can run through the multiple choice questions probably in 15, 20 minutes, a half an hour, and it's just a good review of a broad range of topics like electric field lines, conductors in static equilibrium, all that stuff. It's an enormous amount of material, but it's summarized and captured in the multiple choice questions. And so it's a good way of reviewing and just cementing your knowledge of each subject area. And especially for the final exam, look at those multiple choice questions on Ampere's law, on Biot-Savart law, on Faraday's law, on capacitance, on inductance. I think it will really help you learn and integrate that material. The other thing is, of course, problems. So go and get the midterm exam, and let's do problem number 4. Get the midterm exam and see if you can do problem number 4. Very few of you actually did the problem well. So look it up and try doing it, and then come back and see what I do. Okay, I'll give you one more chance. Don't be lazy. If you don't try doing this, you're going to just end up doing the same thing you did on the midterm and not be able to do it. It takes effort on your part to learn how to do these things. So pause the video and do as much of the problem as you can, and then compare what you did to what I did and see how to do it. Alright, so first thing, it tells you, draw a clear label diagram. That's so important. So I have the two charges. I put what the charges are. I labeled them Q1 and Q2. I put down the distance, it's centimeters. I put down the distance. And now we want to what? What are we doing? This is where you get confused. You start calculating force between these two charges. Nothing about force. What we're trying to find is, at this point, the electric field. Why is there an electric? Because this charge has an electric field. So there's an E1, and that goes toward the E2. This should be in your figure. At this point, there's a field due to charge 1. That goes away from the charge, so that's E1. So we're adding two vectors. The vectors should be there. They should be labeled E1 and E2. And then you should be writing down, what are we doing? We're finding E at point P. E at point P is going to be the sum of two vectors, E1 plus E2. But they're vectors. We have to add them like vectors. So what is E1? Okay, now we need, for a point charge, we find the equation by K, Q1 over R1 squared. So I'm just going to write the symbols, right? K, we know what it is. It's 8.99 times 10 to the 9th, blah, blah, blah. Q1, we know what that is. We'll put the numbers in a minute, but I'm going to write it. Q1 over R1 squared. Now that's the magnitude, but it's a vector, so you have to add it. So you got to put in the I hat. It's in the I hat direction. Whoops. This should go over here. Let me see if I can move that. No. Anyway, I'm getting too excited. So this is E1. Goes here. And E2 is what? It's K Q2 over R2 squared. And what direction it's in? It's in the negative I hat direction. So this is kind of easy problem. It's not like you got a point where there's three vectors and you got to find the components of every vector and add them. It's not complicated like that. It's a simple one-dimensional problem. You simply need to find E1 and subtract E2. And if E2 is bigger, the answer is going to be negative. If E1 is bigger, the answer is going to be positive. Okay, and this is how you do it. So let me try doing that, writing it down and see what you get for an answer. And I'll do the same thing. You come back. So here's where you have to be careful and methodical. You see how I made mistakes earlier. So once again, I'll give you one of these problems. I'll ask you to draw the figure. I'll ask you to write this equation. And I'll ask you to show your work. So notice, I put down this plus this. Actually, strictly speaking, I should have absolute value signs here. This is a positive charge, and the field is positive. This is a negative charge, and the field is negative, but I put in the negative sign. And remember, a negative charge on this side would have a positive field, so you got to be careful about the direction. You got to get it from your figure. So if I take the magnitude of these two things and subtract E2, it will be either in the positive or negative I hat direction. Now how do I get this? There's K, there's Q, and there's R1. R1 is what? Remember, we're calculating the field at this point. So R1 is the distance from the point where we're finding the field. This is where you get confused, I know, to where the charge is. So for E1, the charge is 30.8 centimeters away. Of course, we have to put that in meters, and we got to square it. And by all means, I don't do this accidentally. I do it on purpose, that the 10 to the 9th and the 10 to the minus 9 cancel. And so you just need to take the 8.99 times the 3.28 and divide it by the 0.308 squared, and that will give you this number. Now what are you going to do over here? You're going to do the same thing. This is going to be 8.99 times 10 to the 9th. This is going to be, just put the number in because we have the negative sign here. 1.37 times 10 to the 9th. They cancel. The 10 to the minus 9, 10 to the 9th. And what's the distance? Again, be careful. It's the distance from Q2 to the point, or from the point to Q2. This is where we're not calculating the force between these two charges. We're treating these two charges separately. Okay, and then when you add those two numbers, the answer's posted. I don't need to give it to you. It gives you the answer. Okay, now we have to find the electric potential here. So go ahead, see if you can do that. Okay, first of all, potential is the electric potential energy per unit charge. So when we talk about the potential at point P, there's no energy. There's an energy between the two charges, but we're not asking for energy. We're asking potential at this point. Just like there's no force, but there is a field. There's no energy, but there's an electric potential, like the energy field. So at point P, I can't draw them as vectors because they're not. At the potential at point P is going to be the sum of the potential at this point due to this charge and the electric potential at this point due to this charge. These are scalars, not vectors. And what's the equation? Well, the equation for potential due to a point charge is KQ1 R1. So we have the same thing, the 10 to the 9th and the 10 to the minus 9th. The nanocoulombs are going to cancel. It's simply going to be the 8.99 times the 3.28 divided by what? Again, this distance. We're calculating the potential at this point due to this charge, so that is the relevant distance. And since the charge is positive, the potential's positive. Again, it's not a vector. The potentials are actually much easier because they're scalars. And then this is negative, so the potential here is going to be negative. So I put a plus sign here because I'm going to put the negative here. But you should know that this is going to be a positive number and this is going to be a negative number. And it's simply KQ2, so the 8.99 times the negative 1.37 divided by what? The distance from that charge to that point. And that's how to do these problems. And be ready. Don't be surprised if you see a problem like this, or a little bit harder, such as a two-dimensional problem. Suppose we have two charges, positive, a negative charge of a different value, twice as big or bigger. 3 centimeters apart along the y-axis. 4 centimeters away along the x-axis is a point. What's the field here? The field here is going to be a vector this way from that charge, and a vector this way. This has no y component. This, you got to find the components. You got to add the x components, the y components. It's a lot more complicated, right? But you should be able to do it. This is like vectors from first semester. This would be, if this is Q1 and this is Q2, this would be E1 and this would be E2. And it's the same thing. E total is going to be the vector sum of E1 plus E2, but you have to worry about components in this case. And if you want the potential here at this point, remember, they're not vectors. The potential is just going to be V1 plus V2. And if this is 3, 4, then this is 5, right? And this distance you have to have. Because what's the potential at this point due to this charge? It's going to be K Q1 over R1. Potentials, it's not squared. If it's a field, it would be squared. So you have to have that distance from the charge to the point. And if it were the field, then this would be squared. You'd get this value, and you'd have to get the x and the y components. You'd have to find that angle. And it's a 3, 4, 5, so this angle is going to be 36.9, right? You have to do all that trig. So you see how much easier the other one was. But you should be able to do this. And remember, field are vectors, potential are scalars. You just add the numbers according to the sign of the charge. Okay, that's enough for now.